is tomorrow is election day, and I don't want to like talk a ton about this, and I'm very specifically told not to talk about partisan type things, but I think what I think is reasonable to say, and I'll just leave it at that, is pretty clear that right now, like, direction of the country is, people are split into two pretty different ideas of where we should go as a country. And people over 65 all vote. Like, they vote at an incredible rate. And people between 18 and 44 vote at a very low rate. And what that means is that people over 65 are deciding the direction of a country that you're going to have to live in for a long time, and they're not going to have to live in very long. And so just please, please vote if you haven't voted yet. It's a matter of life and death for a lot of people. So if you, I know the younger you guys are, not all of you are super young, but the more you move around and maybe you don't know where your polling place is or whatever, this is a really nice website, Vote 411. It has everything that you need to find out where you need to go. In Minnesota, there's same-day voter registration. So you can find here what you need to bring to the place so you can vote. But that's all. It's the most important thing going on this week, way more important than pulling things around on cables through pulleys. Okay, so last time we were talking about police. And we did a bunch of problems where there were two objects connected together, and you're seeing like what's the acceleration of the system when one object's pulling the other one the other way. There is an approach that's going to be useful. So we'll use this approach. Um, anytime an object is rolling or sliding along a surface, and that is that we'll put the y-axis pointed directly out of the surface, perpendicular to the surface. Mm. And the x-axis then has to be parallel to the surface. So for example, if we're doing a problem with an incline like that and two objects pushing against each other and there's some force here or something, we're going to always have the y-axis point straight perpendicularly out of the surface, the x-axis parallel to the surface. Okay, and why is this useful? So let's think about the benefits and the costs of doing this. Because really, this is the first time since we did the problems that were just straight vector problems, um, that was the last time that we ever used a coordinate system that didn't have the y-axis pointing up and the x-axis horizontal. But now that won't be the case anymore for if the surface isn't, I mean, if the surface is horizontal, then we'd still have the coordinate system we're used to. But if the surface is at any kind of incline or even vertical or upside down, in all those cases, we're going to use like a funky coordinate system. So why are we going to do that? First of all, as far as benefits, what this means is that the acceleration of the object is always going to be along the x-axis. So the acceleration vector is always just going to be, we'll always just write it as a0. So that's pretty nice. That's nice. You don't have to think about what direction it's going. We know that it's going to be able to move parallel to the surface, and parallel to the surface is going to be our x-axis. Right. What else? Well, any forces that are parallel to the surface will also have only x components. So you can imagine a lot of times, like look at this example up here. The contact force between these two objects is going to be perpendicular to the surface of contact, which means it's going to be parallel to the surface. So both of those two contact forces, whichever one of these we isolate, is going to be parallel to the surface. This 500 Newton force, just a lot of times there are forces that are parallel to the surface. So what are the costs? There's one, oh, let me say one more. The normal force applied to the object by the ground, it's always going to be straight out of the surface, which means it's always going to be the vector 0, positive, n. Okay, so like you can see the acceleration vector, you always know what it's going to be. You don't even have to think about it. I mean, really, the benefit of, and the normal force vector is always going to be 0, n. The real benefit is that every single problem, those appear the same way. So every problem just sort of reinforces that to you. It leads to a lot of mistakes if you have to treat different problems different ways. So this is a nice thing. Okay, there's one cost, and that is weight force that always used to be just 0, negative, whatever, mg. Now it's going to get complicated. So how is that going to be represented? Think about it like this. If you have a coordinate system like this, and the weight force points straight down, so the weight force has a magnitude of mg. That always used to be along our negative y-axis, but it's not anymore. And so how are we going to calculate that? We're going to have to figure out the angle from the positive x-axis to the weight. So that's theta. And then that weight force is going to be mg times cosine theta sine theta. Okay, so a few things are easier in this rotated coordinate system. One thing's harder, so all things considered, this is helpful, but it does make dealing with the weight, we've never really had to worry about dealing with the weight before. Now we're going to have to do a calculation every time for that. Okay, so let's do two examples. We'll do one where there's a pushing force and one where there's a pulling force. Anybody have any questions about this yet? Yep. Yes. Well, you can do it in radians. I would recommend degrees. That's how the problems are going to always be given. But if you do that angle in radians, it would work like that too. In this class, I think just always keep your calculators in degrees. There's never a time you need to use radians in this class. I can usually tell, like on a test, if you enter in cosine and sine of 30 or whatever, and it's in radians, it's usually pretty obvious to me that that's what happened, because you get these wacky answers that, don't really relate to anything. And I don't take points off for that. So I don't know. But try me. I mean, there could be a time that I did. I don't grade the same every day. Um, okay, so first, let's do an incline like this. And two carts pushing against each other. And let's say this one is 20 kilograms and this one's 5 kilograms. And let's say the angle that this incline, it looks like it's curved, but it's supposed to be straight. Let's say the angle there is 30 degrees. I'm going to put it at the top. It doesn't change anything. Like if I did it like this, or oh, you mean like this? Oh, okay. Yeah. So this, if any of you some of you have studied for the SATs more recently than others, but one of the things that is in your little SAT study book is that if you have um, if you're looking at the angle here and the angle here, I forget what they're called, vertical angles. Uh, anyways, those two angles are the same. And so if it's 30 degrees from the horizontal down here, it's 30 degrees from the horizontal. Well, yeah, I mean, but I measured this one going up and this one going down from the horizontal. So I could have written it either of those two ways. I tend to draw it like this. I don't want to make this like a geometry class, so I don't try to make that stuff confusing or whatever. But as you saw, a problem someone else gave or whatever, this means the same thing as this. Yeah, there's a name for those. And then this angle here is the same as this angle here. Alternate angles or vertical angles or something. Because either way, we would use a coordinate system with the y-axis pointed out of the surface and the x-axis, whichever direction parallel to the surface, gives us a coordinate system that makes sense. It has to be a rotated version of the usual coordinate system. And yeah, those mean the same thing. Yeah. Well, like I said, in my problems, I tend to always put them at the bottom. I mean, okay. Okay, and let's say that there's a force applied this way. Let's say that's 30 newtons. And let's say we want to know what's the force vector applied, let's say, to the, on the 5 kilogram cart by the 20 kilogram cart. Okay, well, in this kind of problem, anybody remember, I think I said this at least once before, what's the first step that we usually want to take in a problem like this? That's right. And what's the body that we want to isolate? What's the chosen body? So if we chose the 5 kilogram box, we would see that there were two unknowns when we got to Newton's second law. It's not wrong. You can do it that way, but it's not the quickest way. So you'd isolate this one, you go to Newton's second law, you'd have an unknown acceleration, and you'd have an unknown force pushing on it from the 20 kilograms. So then you'd have to isolate something else. And, so instead, the way to go on these, if you don't know the acceleration, is to isolate both of the two things together. Do the whole system as one. Use that to calculate the acceleration. Once we have the acceleration, then we'll go and isolate the 5. Okay? Okay, so first thing we're going to do is a free body diagram of both of them. There is a weight force going down. That's equal to 25 times 9.81. So that's 245.25. And now we have the weight force in there. So now we're just going to go around the boundary looking for contact with the boundary from the surroundings. First, there's one at the wheels, and I'll lump them all into one here. And I'll call this the normal force, or the maybe total, in total. And one thing I want to point out, and this is a good habit to get into, from the free body diagram, you should be able to tell what vectors are parallel to each other, what vectors are perpendicular to each other, and what vectors are neither of those. Okay, so this is could maybe be a little more clear, but it's pretty easy to tell that I don't mean for those two vectors to be parallel. And then keep going around the boundary, and the only other place that there's a force applied to the boundary is over here, and that's the 30 Newton force. We don't know where that's from, but it's given. And then there's nothing else. Go all the way around, get back to the wheels, so you're done. Well, representing the normal force is going to be easy. That's always just, in this case, it's going to be 0 N total. That's how that always appears. The 30 is going to be easy. That's pointing in the negative x direction, so that's just going to be negative 30, 0. But we do have to deal with the weight force. That's going to be more complicated. So let's do that first. So here's the coordinate system. And the weight force is just straight down. And it has a magnitude of 245.25. And what we want is this angle here. Okay, so what we really need is the angle. In order to figure out this total red angle theta, we need to know the angle between the negative y-axis and the weight force. Anybody have a feel for what that would be here? It's just going to be 300. So the angle between the negative y-axis and the weight force is just this 30-degree angle. Okay? And whether you're at, whether you have to go past the 270-degree line, the negative y-axis, or whether you don't quite get to it, has to do with which way the incline is tipped. But physically, if you're having trouble seeing why that is, I always think of, so imagine this being the original coordinate system. Okay. And then our new coordinate system is tipped like this. Okay. And so before we tipped this usual coordinate system, the negative y-axis was in line with this. We had to tip it 30 degrees to make it line up with the coordinate system we want, which had the effect of tipping the negative y-axis 30 degrees away from that one. Anybody have any questions about that?
So that number will always be given?
The 30 will always be given, yeah. And you just have to, really all you have, whatever this angle is from the horizontal is going to be the angle that you're going to have to go from the negative y-axis to the weight force. But it's sort of up to you. You're going to have to figure out on your own, which is basically is the weight force in the third quadrant or the fourth quadrant. And that has to do with which way the incline is tipped. You could have an incline this way, or you could have one this way. Yes. It would not make a difference in how we treat it, but the values that we calculated would be different. And actually, when I say going up, it would make a difference if it was accelerating up versus accelerating down. But remember, I think I mentioned this last time. Maybe it was the day class, though. The velocity of the carts doesn't have any effect on it. And that's hard to get used to. But there's nothing in this problem that says these carts are at rest at the instant we're looking at, or that they're going down at 15 miles per hour or going up at 2 miles per hour. And the answer that we're going to get for the acceleration and the forces would be true no matter what the velocity is at this instant. The velocity doesn't have anything to do with forces or accelerations. So this angle here is 30 degrees. And that means that our theta is, so you go 90, 180, 270 plus 30, so 300 degrees. And so the weight force is 245.25 times cosine and sine of 300 degrees. So now let's go to Newton's second law. And we have the easy stuff. We have 0 n total. That's how the normal force always appears. And then the 30 Newton force is in the negative x direction. So that's negative 30, 0. And then we have the weight force, and that's 245.25 times the cosine of 300 and 245.25 times the sine of 300. And all that is equal to the total mass times the acceleration vector, which is easy, it's always the same. Can someone calculate that? Tell me what that vector comes out to. Negative 212.39. And this one is just, what? Yeah, that's the, and then this one is 122.6. Thank you. Okay, so we have an x equation and a y equation. The x equation says 0 minus 30 plus 122.625 is equal to 25a. And so 92.625 is equal to 25a. And so what do you get for a? 3.70. Okay, 71 meters per second squared. And then if you wanted to give that as an acceleration vector, I didn't ask for it in this problem, but the acceleration vector would just, you would take this number and plug it back into the acceleration vector that we had. You know, this right here is the acceleration vector. So it's equal to 3.710. Or another way to say that is 3.71 in the positive x direction. And the positive x direction is this way, you know, aligned with the surface. Any questions about that part? So now we know the acceleration for each of the two individual carts. So now we can isolate the individual one. So free body diagram for the 5 kilogram. There's a weight force with a magnitude of 5 times 9.81. So that's 4.905. Nope, 49.05. And then going around the boundary, there's a pushing contact from the ground. I'll call that N5. Keep going around, and then you get to that 30 Newton force. Keep going around, and when you get to the left side, that's where it's in contact with the 20 kilogram cart. So there's a pushing contact there. So what's the direction of the pushing force applied to the 5 by the 20? Yep, toward the body. And I'll call that capital R for reaction force. And now Newton's second law. Well, last time I did the thing to figure out the angle for the weight force. What's the angle going to be this time? It's going to be the same, yeah. And that's how it's always going to work. If you're like in a single problem, the weight force vectors are always going to be pointing in the same direction, you know. And so, yeah, theta here is going to be 300 also. It's just going to be multiplied by 49.05 instead of by 245 or whatever. Okay, so Newton's second law. The R force vector is in the positive x direction, so that's capital R0. The normal force is what it always is, 0 N5. The 30 Newton force is in the negative x direction, so that's negative 30, 0. The weight force is 49.05 times the cosine of 300 and 49.05 times the sine of 300. And all that's equal to the mass of the body, so 5, times the acceleration vector of the body, 3.710. And so the x equation here says r plus 0 minus 30, and then 49.05 times cosine of 300 is just half of 49.05, so that's plus 24.525 is equal to 5 times 3.71, which is 18 point. What? 5.5. Okay, so then now we can just calculate R. So R is equal to 18.55 plus 5.475, right? What's that? 24, what? 025 newtons. Okay, we have the R vector. Well, we don't have the R vector. We have that number R, the value of that variable. What we want is the force vector that's applied to the 5 by the 20, and that's this. You know, on the 5 by the 20. And so now we just plug that 24.025 into this vector, and we get that the force on the 5 by the 20 is equal to 24.0250, or that's also a vector along the incline like this with a magnitude of 24.025 newtons. Any questions about that? Okay. So, the only thing that's really new with problems where you're not rolling along a horizontal surface is that now you have to find an angle and use cosine and sine for the weight force. Everything else is really pretty much the same thing we've been doing. Okay, now let's do an example with a cable and a pulley. And actually, this is very much like a lab, not the lab next week, but maybe the lab after that. So make a mental note of this or whatever. This is a calculation that we're going to have to do in lab in a couple weeks. So let's say we have an incline like this. And we have a cart rolling along this surface. I want that cable to be parallel to the surface. And then on the other side of the pulley, that cable is supporting another mass. And let's say this is 1 kilogram, and let's say this is 0.5 kilograms. And let's say that this angle is 20 degrees. And we want to know two things. And we're not really going to do them in order. I think we're just going to have to sort of solve them together. But and second, what's the acceleration of the cart? And this is one of the first ones actually where there's no way to figure out just from eyeballing this what direction the system is going to accelerate. Maybe this is enough weight to make this accelerate up the incline, but maybe it's not, and it's going to accelerate down the incline. So we have to calculate that to know. Okay, well, so to do this problem, we're going to have to isolate each of those two masses, and we're going to have to solve it as a system of equations. We did a problem or two like this last time. The only difference here is that this time when we isolate the 1 kilogram cart, the weight force isn't going to be directly in the negative y direction anymore, so because we're going to be using the rotated coordinate system. Okay, so I'll start with a free body diagram of the 1 kilogram. There's a weight force acting down. Okay, we'll do them together. So whenever there's a pulley involved, you can't really do them together. So yeah, that's a good question. So It's only when they're directly in contact, uh, rolling or sliding along the same surface that we isolate them together. Yeah, if you know the acceleration beforehand, you don't ever have to. Okay, so there's a weight force acting down. 1 kilogram times 9.81 is 9.81 newtons. And then there's a normal force pushing up straight out of the surface. So I'll call that capital N. And the only other contact is the pulling force from the cable. So I'll call that T. And then here's the coordinate system. Weight force is straight down. And so the angle between the negative y-axis and the weight force is 20 degrees. The angle we want goes from the positive x-axis to the weight force. So what's that? 250. Yep. It's 20 degrees short of getting to that negative y-axis. So Newton's second law says we have 0n plus that cable force is in the positive x direction. So that's T0 plus 9.81 times the cosine of 250, 9.81 times the sine of 250. And all that's equal to the mass times the acceleration that always shows up the same. Can someone tell me what this vector is? Oh yeah, 20 degrees, right? 3.36, okay. 22. Okay. So the x equation here says 0 plus t minus 3.36 is equal to 1 times a. And so I'll just rewrite that as t is equal to a plus 3.36. And I'll set that aside. We'll come back to it. We know we can't do any more with it because it's a single equation with two unknowns. And so now I'm going to isolate the hanging mass. And you might think it would be reasonable to think that you have to use the same coordinate system for both of these two things. But if you think of it this way, I think it sort of makes sense. We're going to do, basically, we're going to do separate analyses of the rolling mass and the hanging mass. So we can use whatever coordinate system we want for both of those. And then when we get done with those two analyses, both of the equations that we get are going to have to be true. So both equations have to be satisfied, and it doesn't depend on those having the same coordinate system. So for this one, we're just going to go back to coordinate system that we're used to, the usual coordinate system. That's because it's not rolling or sliding. Okay, so there's a weight force down that's equal to 0.5 times 9.81. And then the only place the surroundings make contact with the boundary is at the cable. And that has to be a T because it's the same cable as the cable in the first part. Now Newton's second law says 0 positive T, because it's in the positive y direction, plus 0 negative 4.905 is equal to the mass times the acceleration. And now we have to think about, so when we define the acceleration of this one, we call it A0. So we have this one going, say, think of this one going an inch in its positive x direction. Which way does this one go if this one goes an inch in its positive x direction? Yeah, this one goes in its negative y direction. So we're going to represent the acceleration of this as 0, negative a. So the y equation here says T minus 4.905 is equal to negative 0.5 a. So we had that equation star. I'll call this one equation 2 star, and that's our system of two equations for two variables. So if I substitute, this is from equation star, we know T is equal to A plus 3.36. So I'm going to substitute that into this equation. And now equation 2 star becomes A plus 3.36 in place of T minus 4.905 is equal to negative 0.5 A. And so what's 3.36 minus 4.905? 1.545, and that's equal to negative 1.5 A if I subtract A from both sides. And so what do you get for the value of A? Right about 1. Yes. Why didn't I solve for T? I could have if I would have. So what I have to do is I have these two equations that have two variables between them, and I have to solve them for T and A. And I can do it in either order. This is just the order that I chose because I had this written, I had expression for t here, so it was easy to substitute it in there. But we'll go back and find t after we find a. Anybody have that number? 1.03 meters per second squared. And now that we have that, we can calculate t. So t is equal to 1.03 plus 3.36, so 4.39. Okay, we got an a value of 1.03 positive. So what does that say about the acceleration of this system? We got a positive 1.03. And so if we plug positive 1.03 into this vector, we get that it's moving in the positive, its positive x direction, which is up the ramp. Any questions about that? That's a hard one. I don't think there might be late actually on the practice problems. There might be one sort of like that, but that's not what the problems are going to be like to start with. Yeah. Right. Yeah. So we don't know which one, but all we have to do to get this problem right is just choose the right dimension, x or y. And on these sliding and rolling problems, that's easy. It's always going to be x. So you just write it as positive a0. And if it ends up being negative, that negative will just come out in the answer. So in the end, it'll tell you. Right. Okay. Yes. So how did we? Okay. So in the first one, we said arbitrarily, we're going to make it so that if a comes out positive, it's moving in the positive x direction. And then all we had to do when we go to the second one is be consistent. So we're saying if the variable a is positive, it's going to move up the ramp, and that's going to make the hanging mass move down. And so that's the consistency that we needed. And so if it came out that a in fact wasn't positive, it was negative, that would say this is moving down the incline, and it would say that this is moving up, and those are still consistent with each other. Any other questions about that one? Yes. Yes. Yep, that's right. And in a way, I mean, that's sort of the same thing that I would have done if I would have just isolated them in the other order, you know. Yes. It's either one because so we get that this variable a is 1.03, and if we would have plugged it into the acceleration vector of the hanging mass, we would have gotten the acceleration vector 0, negative 1.03, which still corresponds to the rolling one going up the ramp. Yeah, that's right. Any other questions right now? Okay, let me give you a problem to work on together, and I'll give you some time to work on it, and then I'll go through it. It won't be like that one. Okay, so let's say that we have an angle of 30 degrees for the ramp. And we have a 1 kilogram cart connected by a cable to a 2 kilogram cart. and then they're both being pulled toward the top by a force of, let's say, 10 newtons. And we want to know first, what's the acceleration of the system? And second, what's the cable tension on the cable between the two? Okay, so see if you can think through that. And I know a lot of people are going to get stuck right off the bat, so talk to each other about it. Ask me questions if you get stuck, but see what you can, how much you can work through that, and then after you have a little time to work on it, I'll go through it. So I'm going to go through it now. So first, we're going to isolate the two carts together. So there's a weight force. The total mass of the system is 3 kilograms, so that's 3 times 9.81, so 29.43. And then there's a pushing contact from the ground. I'll call that N total, NTOT. And then the only other force is the 10 Newton force. And the weight force has a magnitude of 29.43. This angle is 30 degrees. And so the angle from the x-axis to the weight force is 270 plus 30, so 300. And then Newton's second law, the 10 Newton force is in the negative x direction, so negative 10, 0. The normal force is always 0, n. And then the weight force is 29.43 times the cosine of 300, 29.43 times the sine of 300. And that's equal to the total mass times the acceleration that we always start out the same, just a0. What do you get for the weight force vector? Okay. Okay. So then the x equation says negative 10 plus 0 plus 14.72 is equal to 3a. So 4.72 is equal to 3a. And so what do you get for a? 1.571? 715. Oh, okay. Okay. That's like exactly half pi. Isn't that creepy? Okay, so the acceleration vector you get by putting that value back in here. So the acceleration vector is 1.571. And now we can isolate one of the two carts. And it actually, in this case, doesn't matter which one, because we're just trying to come up with the magnitude of that cable force. And so if you do it right, and you can try this if you're looking for extra practice on this kind of stuff. So I'm going to pick one of them. Try picking the other one and make sure you get the same value for T. It should work out. So free-body diagram of, let's say, the 2 kilogram. There's a weight force down that's equal to 2 times 9.81, so 19.62. And then there's the normal force pushing contact from the ground. I'll call that N2. And then there's a pulling force from the cable that's between the two carts. So that's going to be this way, and I'll call that T. And then there's the 10 Newton force this way. So Newton's second law says that 10 is in the negative x direction, so negative 10, 0, plus 0 N2 plus T0. And then we have to deal with the weight force, so that's 19.62 times cosine of 300, 19.62 times the sine of 300. And that's equal to the mass, 2, times the acceleration, 1.571. What do you get for the weight force? Okay. And so now the x equation says negative 10 plus 0 plus t plus 9.81 is equal to 2 times 1.571, 3.142 pi. It doesn't matter. We could have chosen either one. So I was saying if you have time to look at it later, try isolating the 1 kilogram card and make sure you get the same thing for T, because it needs to come out the same. T should always be positive. If T ever comes out negative, something went wrong in the calculation. Yep, and it would be facing the direction of the 10, and so it would be negative T0 in that case. So then it would come out positive. Yes? No, that's fine. If you can see that, and I think for some people it's sort of nice to see everything just get put in the same way, but yeah, feel free to skip that if it makes sense to you. Okay, so this comes out to be negative 1 point, nope, 0.9 plus t is equal to 3.142. And so that is t is equal to 3.33. newtons. Any questions about that? And so the tension, if you have a problem that asks you for the tension, that's just asking for that number, and it's always positive. If it asks for the force vector that a cable applies to something, then you have to plug it back into the, so like if I wanted to know the force vector that cable applies to 2 kilograms, you take the value of 3 point whatever that we just calculated and put it back into this vector, and that would give you the force vector. But the tension is just a positive number. So the force vector is calculating a force that's applied to some object. The tension is just the number that it's like the magnitude of any force vector that cable applies. That's not an understanding thing as much as just like a sort of vocabulary thing. That's just how people talk about the tension. Yep. Yeah, what did we got an acceleration of, yes. So no, our acceleration vector is in the positive x direction, and our positive x direction is down the incline. So that 10 is not enough. So even with that being applied, it's accelerating down the ramp. 1 pound is like 4.25 newtons. So 10 newtons is 2 pounds or something, a little over 2 pounds. Yes. Nope. No, because it's not on the boundary of the 1 kilogram. Right. So it would be, so yeah, you'd have 9.81, and the normal force, call it N1, and then T, and then Newton's second law would say negative T0 plus 0 N1 plus, now you have to do the cosine and sine, is equal to the mass of 1 times the acceleration. And yeah, if you do it right, it comes out the same. Any other questions? Okay, well, we'll start at 7:30 for the people who are doing lab tonight. And like I said, it's going to be 30 to 45 minutes, and I'm just going to carefully go through all the problems on the lab exam. And so if you have any questions about things you got wrong or whatever, get them ready, and we can talk about that as we go. Okay. Oh, yeah. That was really weird. Well,